Okay, hi everyone. Welcome to the class. It's so nice to see so many people here. It's about 28 people here. The numbers are usually far less, but yeah, that's nice to see. All right. How? I'm just wondering how many of you are first years here. Can you respond in the chat? Okay, one, two. All right. I see. All right. I think there are. I see a lot of first years here. Um, I hope that you guys know that this is not a beginner number theory class. Like there is stuff to be done before this class. If you're studying number theory for the first time, this is not the class for you. Maybe. All right. Uh, all right. Let's start then. Before I start, another thing that I will be using a whiteboard app, and I will be using my mouse for that. So I apologize for my bad handwriting. Okay, is my voice breaking? All right. Yeah. Is it better right now? Is it any better right now? All right, sure. All right. I think I need to be closer to the laptop. Yeah. The uh, I apologize for my handwriting, but other than that, I think we should be fine. Again, so since I will be screen sharing, if you guys have any doubts, you can just unmute yourself and say whatever you want. Since I won't be seeing the chat. All right, let's start then. Can you guys see the screen? All right, sure. Let's start. Um, okay. All right, so the topic for today is intermediate number theory. So the topics which we will be covering are a lot. So we will be going pretty fast today. So I might be skipping a few proofs here and there, and I will be writing very less stuff here because it's hard to write with a mouse. I'm sorry, yeah, with a mouse. So yeah, let's start. So the topics are Fibonacci numbers, Lucas theorem, Chinese remainder theorem, extended Euclidean GCD algorithm. So I assume that you guys know the Euclidean GCD algorithm already. Uh, Apart from that, Fermat's little theorem, Miller-Rabab. Yeah, so this is not there today. Euler Totient function, multiplicative functions, and Mobius inversion and Dirichlet convolutions. Yeah, so that might sound like a lot of stuff. It is a lot of stuff. So we will be skipping proofs, but the proofs are simple enough, so you can look them up online if you're interested. All right, let's start. So yeah,
Excuse me. Yeah, just asking which branch of CS do we use all these mathematic theorems in?
um,
Like, is it used in algorithms or something? I'm not
Um,
sure. I'm new.
in general, if you're attending this class, you would be probably interested in competitive programming. So,
Yeah,
in competitive programming is a fair bit of math as well. So,
right.
the number theory that I will be teaching is very specific to competitive programming. There's a lot more out there, but it is not relevant to competitive programming. So, yeah, that's about it. All right,
Okay. Yeah,
sure.
thanks.
Uh, let's start. So, Fibonacci. Okay. Yep. All right. So I guess most of you know the definition of Fibonacci numbers, but just to reiterate, I will go again. So f1 is equal to 1, f2 is equal to 1, and the sequence is recursively defined as fn equals fn minus 1 plus fn minus 2. for all n greater than equal to 3. I guess everyone knows this already, but even if you don't, that's how it is defined. And this is probably one of the most interesting sequences out there in competitive programming or in computer science in general. So let's see how this works out in how is this interesting. All right. So the first property of Fibonacci numbers, I hope you guys are writing this down somewhere. So it is the sum of first n Fibonacci numbers, of course. The sum of first n Fibonacci numbers, this value is equal to fn plus 2. Yeah.
I'm sorry to interrupt,
Yeah.
but could you record this if possible?
Yeah, it is recording.
Okay, thank you. So you'll post this after
Yeah,
the session's
yeah.
over, right?
I am recording it. I will try and upload to YouTube after this.
Thank you very
Sure.
much. Right.
So it is fn plus 2 minus 1. How this comes out to be is pretty simple to see. So we saw that any Fibonacci number can be expressed in terms of the sum of the previous two Fibonacci numbers. So suppose we can write each fi as fi plus 1, fi plus 2 minus fi plus 1. And this is equal to fi. So if we replace each fi in this formula here with this value, you can see that each fi plus 1 from n plus 1 values will cancel out. So it will be fn plus 2 minus fn plus 1, then fn plus 1 minus fn, and so on till the least part, that would be f3 minus f2 over here. So eventually you will get the value equals fn plus 2 minus f2, and you know that f2 is equal to 1 over here. So that's how you arrive at this formula over here. I guess everyone is clear with this. So any questions? Okay, I'll move on then. So the next identity is this. This one is a pretty relatively unknown identity, but like it might come in useful somehow. I haven't seen it being used anywhere, but it's this. So you can express a Fibonacci number in terms of combinations as well. So, and that is expressed in terms of the nth diagonal on the Pascal triangle. So if we can construct the diagonal, the Pascal triangle in some way, then it would be, yeah. So the nth diagonal would be something like this. This would be the nth diagonal, and this would be another diagonal, and this would be another diagonal. So you can see 1. This turns out to be 1. This one turns out to be 1. This turns out to be 2. Then we would have 2 and 1 over here, and so on, and 1 here. So this is 3. Yeah, so this is a pretty interesting result, but I haven't ever seen it being used. But since in general in competitive programming you're often involved with dealing with combinatorics, so this might come in useful sometime. So this turns out to be, the general formula would be the floor of n minus 1 by 2 minus I minus 1 I for n greater than equal to 1. Yeah, so the first n minus 1 by 2 terms, the sum of n minus I minus 1, Ci, that's the nth Fibonacci number. Yeah, so this is just like a nifty formula. Let's move on to something much.
Excuse me, can you just explain the previous one again? It sounded complicated.
Yeah, just a second. I need to. Yeah. All right. So so this is actually the sum of numbers on the nth Pascal triangle diagonal. So I just made a Pascal triangle. I don't even remember exactly how it looks like, but this is one diagonal. This is the second diagonal. This is another diagonal over here, and this is another diagonal over here, 1 3 3 1. So of course you guys know what Pascal triangle is. So it is the first row is 1 0 C0. The second row is 1 C0 and 1 C1. The third row is 2 C0, 2 C1, 2 C2. Then 3 C0, 3 C1, 3 C2, 3 C3. So it is the sum of numbers on the nth diagonal. So this is the first diagonal. So this is 1. This is the second diagonal. This is 1 again. This is the third diagonal. This is 2. So I just wrote down that formula as saving you all the manipulation and all. That's the formula which comes out to be after that. Did that clarify what I meant?
Yeah, is it n minus half
n
or is
minus
it
1 by 2.
n minus
n
1 whole
minus
by
1
2?
complete half.
Okay, yeah. And one last thing, we get the diagonal by moving one right and then moving one up and right,
Yeah.
right? Yeah, okay. Yeah, thanks.
All right. Let's move on. So now we come to this more interesting identities. So this identity is known as the Cauchy's formula. I don't think you need to remember what the name of it is, but this is a pretty famous identity of Fibonacci numbers. So it goes like this. Is equal to minus 1 to the power n. So fn minus 1 into fn plus 1 minus fn square. This is equal to minus 1 to the power n for any n greater than equal to 2, I guess. Yeah. So the reason that this is so interesting is because we arrive at a very interesting result, is that any two consecutive Fibonacci numbers are co-prime. So this bracket thing is the symbol of GCD. We will be using this notation from now. So this means the GCD of these two numbers, and just a second. And this thing. So square brackets mean LCM, and the circular brackets mean GCD. So yeah, keep that in mind. So the GCD between any two consecutive Fibonacci numbers, that's 1, and we'll see how this comes out to be. It's actually easy to see from this formula. So I'm assuming you guys know basic modular arithmetic here. So suppose that the GCD between any two there is some pair of consecutive Fibonacci numbers which do not have GCD equal to 1. Then there would be some divisor d greater than 1 which divides both of these, right? So let's try doing a modulo over this d in this formula. So if we do a modulo d, so suppose fn and fn plus 1, these have a GCD equal to d. Then this value modulo d would come out to be 0 because it divides fn plus 1, and this value would also come out to be 0 because it divides fn, of course. So the left hand side comes out to be 0 under modulo d, but the right hand side would come out to be minus 1 or plus 1 under modulo d, because it's not possible to go 0 for any number greater than d to divide minus 1 to the power n anything. So this leads to a contradiction, and we arrive at that any two consecutive Fibonacci numbers, they have to have the GCD equal to 1. Did everyone get this? Are they in? All right.
Yeah.
All right.
Yeah.
Let's move on. There's another identity. I think many of you might have seen this. This is called the Benet's formula. Again, this might not be very relevant in CP, but yeah. So this works out. You can write any Fibonacci numbers in terms of this value, alpha minus beta, where alpha is equal to 1 plus root 5 divided by 2, and beta is equal to 1 minus root 5 divided by 2. This might not be very relevant in CP because we hardly deal with irrational numbers in computative programming, but yeah. The Binet's formula is not actually this entire thing. There's more to the Binet's formula. There's something called Lucas numbers, but they're not very relevant today. But the Binet's formula gives the Fibonacci sequence as well as the Lucas number sequence. So you might want to look into that later on, but not now. All right,
It's Benet's formula?
B-I-N-E-T, Binet's formula.
Okay, yeah, thanks.
All right. Now let's move on to the next topic. So these are some properties. The way I haven't mentioned how these are used in a problem, but like there's no way to predict these. These would just come. Like in general, if you do a mathematical problem in CP, you would probably need these identities to simplify your equations and all. So it's handy to have these formulas with you. Let's move on to the next topic, which is called the Lucas theorem. Has anyone heard of this theorem before? I very recently found out about this, and I found it very interesting actually. Has anyone in the class heard of this theorem? Okay, I guess not. Let's move on. So the theorem is, if you have to calculate LCM under modulo P, you can write it as N naught M naught, so the combination of N naught M naught multiplied by N by P and M by P. So under modulo P, of course. This entire thing is under modulo P. So what are N naught and M naught here? N naught and M naught are, N naught is equal to N mod P and M naught is equal to M mod P over here. Now, how is this interesting basically? The reason that this is interesting is that we can calculate pretty large NCM values given that our P is very small. So this formula holds for only primes. So P is prime here. Okay, so why is this interesting? Because we can calculate NCM very fast under modulo P. So we can pre-calculate these N naught M naught modulo N naught M naught GCDs. I'm sorry, not GCDs. Yeah, N naught M naught combinations for each N naught and M naught pair possible. Because P is very small, so these values would range from 0 to P minus 1 and 0 to P minus 1 again. So we can calculate them for all possible combinations of N naught and M naught, and that would take P square time to calculate. And now for simplifying big NCMs, we can just do every time we would just use this formula. We would simplify this by flooring with N by P and M by P, and now N would reduce by a factor of P and your M would also reduce by a factor of P. So you can call this method recursively again on N by P and M by P again, and then it would reduce by a factor of P again and by a factor of P again on M, and so you would get a formula. So basically your running time of this algorithm would be P to the power X equal to log equal to max of N comma P N comma M, sorry, yeah. And we have to find this X, so it's pretty obvious that this X is log of max of N comma M. So the running time of this algorithm would be log of max of N comma M, and that's pretty fast for calculating even modulos of N, say N is say 10 to the power 18 or M is say 10 to the power 18. So this is a pretty nice formula, I guess.
Can you explain the max, how you got the max formula again?
Every time you're recursively calling for over N by P and M by P again, right? Yeah. So
Yeah.
every time you're reducing n by a factor of p and m by a factor of p. So eventually your base case would be either n is equal to 0 or 1, and either m is equal to 0 or 1, something like that, right? For the recursion. So x would become, so the time it would take to take to reach 1 or 0, that would be p to the power x is equal to maximum of n comma m, and that would come out to be log of, your x would come out to be log of max of n comma m base p.
Okay, yeah, I
Right.
got it. Thanks.
Yeah. Yeah.
Just one question. So is P being prime, does it have anything to actually with the algo? Can we use something like, do we have to use something like CRT if we want to extend this to non-primes? Would
Yeah,
that be
I think
possible?
it should be. I'm not. Yeah, it should be possible, because you could convert, like, calculate the NCM under. You could take a variable x equal to NCM, and you could calculate these values under
Okay, so
different primes, and then
yeah. So does
combine
the
CRT.
prime mod just come from needing to have the modular inverse for the factorial
Sorry?
calculation, or the requirement that the mod is prime, does that just come from like needing to use mod inverse to calculate the inverse
I'm
factorials
not
or something
sure
else?
exactly. I just saw. So I haven't seen the proof of this formula. You can probably find it somewhere, but I probably not related to that. This is just in general theorem probably. So this is probably
Okay,
related to
thanks.
just primes in general. All right, let's move on. So now we come to a topic which might take some time. This is called the extended Euclid GCD algorithm. So I'm sure everyone knows the general Euclid GCD algorithm. Even people who haven't done CP before, you might have heard of this algorithm, of the GCD algorithm, to find GCD of any two numbers, the long division method, right? To find the GCD of two numbers. Now, how can we extend this algorithm to find a solution to this equation? So if we have an equation something like this, ax plus by is equal to g, and g is equal to the GCD of a comma b. We want to solve this equation. We want to find some particular solution, particular integer solutions x comma y to this equation. The way to solve. I'm sorry, my bad. Yeah. So x comma y. Yeah. So we want to find this x comma y solution to this equation, integer solutions, of course. So the way to do this is called the extended Euclid GCD algorithm. Now, how did this algorithm work? It's pretty it's very similar to the actual GCD algorithm. So if you guys remember, when we end at the Euclid GCD algorithm. Okay, before we get into the algorithm, I hope you guys know that for any equation something like which looks like this, where g is the GCD of a comma b, this would always have integral solutions. This equation would always have integral solutions. So the condition for any equation, any ax plus by equal to c, where a and b and c are all integers, this would have integral solutions if the GCD of a comma b divides c. So this is the underlying property for many of the theorems. So of course the GCD of a comma b would divide GCD of a comma b, so that we know that the solution will exist for this question. So if you guys remember how the GCD algorithm ends, is that we end up at our a value equal to some value, and our b value is equal to 0. In that case, a is the GCD and b ends up being the 0 when we recursively go down. So the way to express this as a particular solution to g would be g into 1 plus 0 into any value, let's say 0, is equal to g. Alright, and now we want to build this up to our actual a and b values. So this is the final a and b values in the Euclid GCD algorithm, and we want to build this up to the actual values of a and b. So we want to see the transitions basically of x and y from so whenever we do the GCD algorithm, we go from the values a comma b to the coefficients B mod A, just a second, not B mod A, yeah, it's B and A mod B. It doesn't matter either way, but for the sake of continuity, yeah. So the coefficients change this way. So suppose we want to compute the coefficients x comma y for a comma b. We want to see the transition of x1 comma y1, x comma y to x1 comma y1. So x1 comma y1 are the values of x comma y for these two coefficients, and we want to see the transition of x comma y into x1 comma y1. We want to express it in those terms. So let's see what happens. So yeah, let's start. So we can initially write the equation as b x1 plus a mod b y1. This value is equal to g. Now we want this a mod b is really like hindering us to do things. So let's write this in a different way. So this would become bx1. By definition of mod, we can change this into a minus the floor of a by b into b and y1 equals g. All right. Now let's try to express in terms of a and b. So let's separate out the terms of a's and let us separate out terms of b's. So this would turn out to be, yeah.
Excuse me. Yeah, this is the extended algorithm to calculate the values of x and y which satisfy ax plus by equal g, right? Where g is a multiple of the HCF of a and b.
Where g is equal to the GCD of a and b. You can calculate it for, you can thereon extend the answer, right? If you can calculate for the GCD, just multiply by the like whatever the quotient is by the division of the GCD.
Okay.
For any value.
Yeah. So can you explain how we got bx1 plus a mod by1?
Yeah. So
I'm sorry, I got lost.
I told that. Let's assume x1 comma y1 is the solution for g. We're trying to calculate the transition from x comma y to x1 comma y1. We're trying to express how the x comma y values change as we go down in the recursion. Did you get that?
So we recursively keep calculating b and a mod b from a comma b.
The Euclid GCD algorithm works in this way, right? That you have a comma b, then you recursively call the same function to b and a mod b, and then you recursively keep going down till your a value becomes till your b value becomes 0, and in that then your answer is equal to a. GCD stored in the a variable, right? So we are trying to build up the answer. So we saw the base case, which is 1 comma 0, x comma y equal to 1 comma 0. That's the base case, and we're trying to build up from the bottom to upwards.
Okay, yeah, I get it. Okay.
So separating out a, we see there's only one term which relates to a, that's y1, and with b there's x1 minus a by b floor multiplied by y1 equals g. So we can see the transitions here. So x transitions into y1 as we go down, and y transitions into x1 minus floor of a by b into y1. Did everyone get this? So we can and our base case is of course 1 comma 0. So we can build up here, and when we go back all the way to the top, when we backtrack all the way to the top, we will get the answer stored in the x comma y variables. Does everyone get this? Is there any doubt? All right, I guess there's no doubt. All right, good. So let's see the code behind this algorithm. Yeah. So here's the code. It's a very, very small function. So here are your a and b values, and you pass by reference the x and y y variables where you want to store the answer. So this is your base case. When your b value is equal to 0, then you just return x equal to 1 and y equal to 0, and you return a. So this function also returns the GCD and stores x comma y in these variables. So you're returning the GCD and storing these values, because we do need the GCD value for further operations, for further levels. So now you initialize an x1 comma y1 variable. You compute these x1 comma y1 values by recursively calling the method, and now using these values the way we calculated. So x was equal to y1 and y is equal to x1 minus y1 into a by b. So x and y are the variables that were passed from above, and you store these values and you return d in the answer. Is everyone clear with how this function works? Okay, I guess everyone is clear with this.
Can you explain the second
Sure.
last line? In the code?
Second last line, this line? Okay,
Yeah.
you remember the transitions, right? The transitions was x comma y changes to y1 comma x1 minus y1 into a by b. Those were the transitions. So the x comma y variables were passed from above in this GCD equation, and you computed x1 comma y1 for these a comma b values recursively again, and then you use these x1 comma y1 values to determine the x comma y values for the values that were passed from above. Do you get this?
Yeah, I get
Alright,
it.
sure.
Thanks.
Sorry. All right, let's move on then. Yeah. So now that we've done with this, let's move on to another thing. So someone mentioned Chinese remainder theorem before. I think Pranav mentioned it. So that's what we're going to do right now. Chinese remainder theorem, short for CRT, short for Chinese remainder theorem. So Chinese remainder theorem is pretty handy because we can solve a system of congruences in one variable using Chinese remainder theorem. So suppose we have one value x equal to a1 under mod 1 m1. X is equal to x is congruent to m2. Excuse my handwriting. Under mod m2, and in this way we have like n congruences, n different congruences here. So it's an under congruence mn. Now how these congruences are related is that these mi's, these are pairwise coprime. So the condition for CRT is that mi comma mj, these should be pairwise coprime for I not equal to j. Alright, and what CRT says is that there always exists a unique solution to x under modulo m, capital M, where capital M is the product of all these mi's. I'll repeat again. So you have n congruences under different mi's, and these mi's are pairwise coprime, and CRT says that under capital M, under modulo capital M, which is the product of all these mi's, x has a unique solution under it. Alright, now what is this unique solution actually? So let's go on then. Let's define some variables. So m is of course equal to the product of all mi's. Mi, capital Mi. So there's small mi and capital Mi. So capital Mi is equal to capital M divided by small mi. So the product of all the mi's except this, except the ith mi. And there's some variable called Si as well. So we will discuss what this variable is, and x is one of the particular solutions to this equation, under like not under any modulo, but in general. Sorry, I'm now confused what just happened over here. So one of the particular solutions to this equation is capital Mi into Si into Ai. So this value computes out to be one of the particular solutions to this equation, and under modulo Mi, under not modulo Mi, under modulo M, this value computes to be unique for any solutions you find for x. When you do a modulo M, capital M on it, you would always get the same value. That's how it's unique. Alright, so let's find out what this SI value is. So SI value is actually equal to the inverse.
Excuse me, can you just show the previous screen again for a second?
Okay, yeah. Should I move on?
Yeah, thank you.
Okay. So what this SI is? So SI is equal to the modular inverse of capital Mi under modulo Mi, small mi. So that it's the modular, it's Mi inverse, capital Mi inverse under mod Mi, small mi. Sorry, mod small mi. How many of you are not aware what a modular inverse is here?
Here it's multiplicative inverse,
Yeah,
right?
multiplicative inverse is in normal arithmetic. In modular arithmetic, modular inverse of a number is it's exactly like multiplicative inverse. So if you multiply this with mi, the value which we will get under mod mi would be 1. So it's the value under mod mi which you get, which you multiply mi with to get 1. So I think most of you would be aware of how to find the like if you're sitting in this class, you would be aware how to find the inverse value of any number under a prime, not any general number, but under a prime it's pretty simple, and that value is equal to, just to recap, so first of all, the modular inverse of a value exists only if it is co-prime with the modulo. This has to be true. Then the modular inverse exists. So for a prime, this value is equal to a to the power p minus 2, where p is a prime under mod p. The reason is this. We will shortly see what the reason is. I think most of you know the reason, but we'll recap when we recap Fermat's little theorem. You'll see what the reason is. So, but can you see that the modular inverse would always exist in this case? For capital Mi, the modular inverse under small mi would exist because so capital Mi is the product of all the mi's except the small mi. And we can easily see that the GCD of capital Mi and small mi is always equal to 1 because all the small mi's are pairwise co-prime. And hence the product, so the product of all the mi's except any one of the mi's is co-prime with that small mi. Did everyone get what I meant just now?
Yeah.
Alright.
Can you explain again?
So the any capital Mi that is equal to capital M divided by small mi. So there would be no contribution of small mi in this. It will be all the other mi's. The product of all the other mi's, and since all the other mi's have a GCD equal to 1 by the definition of the Chinese remainder theorem, which we just did right now, that all the mi's are pairwise co-prime. that means that
Okay, I got
that
it.
means
I
that
got
this
it.
has to have a GCD equal to 1 with it. Alright, let's so how do I if we had a problem where we had different primes, a system of different modulo primes, then it's pretty simple to calculate because SI is directly equal to this value. I'll discuss again how this comes out to be, how this result happens, but it's pretty simple to see so far right now. Yeah. So with that, let's move on to the next theorem.
Can you repeat what P is?
It's a prime. It's any prime.
Equation there.
Like I'm saying that the modular inverse of any number under modulo P, provided that A is co-prime to P, is a to the power P minus 2. Okay. Alright, so this brings me to the next theorem, which is called Fermat's little theorem. I'm writing FLT for short because it will take a lot of time writing Fermat's little theorem here. But Fermat's little theorem is pretty simple. If you have A is a number and P is a number, P is a prime, and the condition is A and P are also co-prime. So P does not divide A, basically. P does not divide A. Then A to the power P minus 1. This is always equal to 1 mod P. This is one of the most famous theorems in number theory, and this is like one of the most extensive results in number theory. So I think everyone can clearly see why the modular inverse would be a to the power P minus 2, because you could always just write it as a to the power P minus 2, and this turns out to be the inverse of A. Is everyone clear with this? Yeah. So alright, so moving on. Now we want to calculate, now let's primes and all are fine, but we might want to calculate the modular inverse under a non-prime modulo. So we have this condition again. So I mentioned that for any modular inverse to exist, they should be first of all co-prime. So for modular inverse of A to exist under modulo M, A and M should be co-prime. And the way to calculate this lies in one of the algorithms which we discussed just now, and that is the extended Euclid GCD. We can use that algorithm to calculate the modular inverse of A under modular M. And here's how we do that. So what we do is in the top method of GCD, we pass the A and B variables. So we pass A as the first parameter and M as the second parameter, and X and Y are as usual. So when you get an answer to this equation, you would get an answer equal to, so you would get some Y value here, of course, but the modular inverse value which you get would be stored in the X variable. This would come out to be A inverse here. And why does this work? Can anyone tell me? Like, is there anyone who wants to tell me why this would work here?
Because the GCD of AM is 1.
Sorry?
Right? The GCD of A and M, we assume it to be 1, right? So when you look at A into X plus Y into M is equal to 1, and then you take mod of M on both sides, you get your modular inverse definition.
Did everyone get what he meant? I'll repeat what he said. Can you turn off your mic? Yeah.
I
Okay.
saw.
Yeah. So what he said was that if you take modulo M on both sides, you would get AX is congruent to 1 because YM is always divisible by M. So it's congruent to 1 mod M. And this X value would come out to be the inverse value here. So x mod m, whatever x value you get, x mod m would be the modular inverse of A under modular m. Everyone got this? And just to like make sure that we do not get an incorrect, so if we can actually just pass without checking that the mod GCD of them is 1 or not, we can just pass them into the equation, and whatever value we get as GCD over here, we can just check if it is equal to 1 or not. If it is not equal to 1, we can say that the modular inverse does not exist. All right, so just to see again, second. Yeah, so here we would pass these values, and we would, in our output, we would get a g variable over here, and we check that g is not equal to 1 here, first of all, whatever, and if it is not equal to 1, then the GCD then the modular inverse does not exist. We can return it from there itself. Otherwise, we can return x mod m. Now this solves the equation ax plus by equal to 1. So it is possible that the x value that you get here is negative. So first, in that case, you would have to take a modulo of x modulo m, and then add m to it, and then take a whole modulo m over here. The reason is that suppose x was negative, so this would x modulo m gives the value, gives the negative value which is greater than minus m basically. So when you do a plus m over it, it would result in a positive value, and if you do a modulo m over it, it would result the same value. In case it is a positive value, it would again give a value which is from in the range 0 to m minus 1. This would give a value which is in the range m to m minus 1, and then a modulo m would give a value which is 0 to m minus 1 again. Did everyone get this? All right, let's move on then. All right, so all this is now we move on to one of the topics which might be interesting to most people here. This is slightly more intermediate, I would say. So Euler Totient function. This is probably the most famous function in the entire number theory field. Euler Totient function, no surprises who made this function. So the function is written like this, phi of x, and it's defined in a pretty simple way. It is the numbers less than equal to x which are co-prime to x. This is so phi of x is the number of numbers which is less than equal to x which are co-prime to x. So that means that they have a GCD of 1 with x. So so for a prime, let's take the easiest case possible. Let's consider the phi of p value for a prime, and all the numbers, by definition of a prime, all the numbers less than a prime are co-prime to it. So the value comes out to be p minus 1 for a prime. Now let's move on to some identities of this function. So the way to calculate phi of x is pretty easy. There's a very simple formula for it. Since we are very short on time right now, I won't be going to the proof of this formula, but you guys can look it up, and it's very simple to see. So the formula is 1 minus 1 by p1, 1 minus 1 by p2, and so on till 1 minus 1 by pk, where p1 all p1, p2, and so on till pk, all these primes divide x. So all the primes that divide x, these are the primes. So p1, p2, pk, those primes. So this is a formula for phi of x for any general x. Of course, for x is greater than or equal to 1, of course. Now, how does this okay, another very good identity is, the second identity is sigma of all the numbers which divide n phi of d. This value equals to n. Again, the proof is, you can imagine this proof some way. I won't be going into the proof, but the idea is to divide the set of divisors into groups, into different groups, and you would see that the size of each group, the sum of the sizes of the groups would come out to be n. Yeah, so the sum of the Euler Totient functions of the divisors of n is actually equal to n itself. So you can see this as a different way to represent n somehow. I don't know anyone who would want to represent any n like this, but let's see. All right. So why study the Euler Totient function? So that we arrive at one of the daddy theorems of number theory, which is called Euler's theorem. Euler's theorem, and theorem is a of phi of m, a to the power phi of m is equal to 1 modulo m, for if a and m are co-prime, of course. Okay, so this is the theorem. So this is true for any modulo m, not just primes. And does everyone see how this manifests into the Fermat's little theorem if we replace this with p? Because we know that this value is equal to p minus 1 for a prime, and this value is equal to p. So this becomes a to the power p minus 1 equal to 1 modulo p. So Euler's theorem is a super theorem for Fermat's little theorem. Right. So this theorem is really useful. And I guess everyone can see now that if you know this theorem and you have the totient values pre-calculated, you don't need to use the extended Euclid GCD method to calculate the inverse values, the SI values for CRT. So the SI values for CRT could just be calculated as power of, we could do a power of for capital Mi for comma phi of small mi minus 1. So this would give us the inverse of capital Mi under small mi, of course, mod m, of course, mod small mi, of course. Does everyone get this? Okay, I think everyone gets this. Okay. Now we move on to a fairly advanced topic in number theory, which is called multiplicative functions. Multiplicative functions is not the advanced topic, but what we do with multiplicative functions is more advanced, I guess. Multiplicative function. You guys might be wondering how all of these things might be used somewhere. We will discuss some problems at the end. So you guys will see how this turns out, how some of these things turn out. So multiplicative functions are functions. So they are by definition, so number theoretic functions. It's just a very fancy name for functions which accept values, integer values, and which accept integer values, which output integer values, and allow modular operations over them. So it's just a very fancy name for that. And the property is that if f is a multiplicative function, then f of m n, this value is equal to f of m into f of n. But there's a special condition over this as well. M and n are co-prime. So you guys might have noticed that everything is very much related to co-prime stuff in number theory in general. Yeah, so that's so these are multiplicative functions. And you guys might notice that one of the functions which we have studied, phi, is multiplicative as well. This is a multiplicative function. You guys can test it out as well. It's pretty easy to see, I guess. So phi is a multiplicative function. Now so how is it multiplicative? I can give an idea. So remember the condition that these two, when we talk about multiplicative functions, we always consider numbers which are co-prime over here. So if two numbers are co-prime, they definitely don't share a prime factor among them. So if you want to calculate phi of mn, you can see that phi of m is equal to x into 1 minus 1 by pi, the product of all these pi's. And both m and n won't be sharing any of the pi's. So eventually that would turn out to be the pi's present in mn into m into n. So that turns out to be mn into the product of all the pi's in mn. Did everyone get this? I think everyone got it. All right. Yeah, I heard someone turning on the mic. Okay, never mind. Mobius, so the most famous multiplicative function is Mobius function. Yeah, so Mobius function has a very cool name, but it's very simple. So mu of x, mu of x is defined as follows. It is equal to 1 if x is equal to 1. It is equal to 0 if there is some prime p for which a square power of it divides x. So basically any number x which has a prime power more than 1 dividing it, that mu of x function turns out to be 0 for it. Otherwise, so if x is of the form of p1, p2, p3, p4, all the powers are 1, the value is equal to p minus 1 to the power k, where x is divisible by k primes. Everyone got the definition of Mobius function? Okay, I think everyone got it.
Can you repeat it once?
Yeah. Okay, so if x is equal to 1, mu of x is equal to 1, 0 if there's any, so if suppose x is of the form 2 to the power 3 into 3 to the power 1, 3 into 5, the mu of x value for this would come out to be 0 because there's 2 square divides this x value. So basically if x has any prime p dividing it more than one time, then that means that the value would come out to be 0 for that Mobius for that value. Otherwise, if there are suppose let's assume that we have the number 2 into 3 into 5, so there's no value dividing it twice here, no prime dividing it twice here, so the value would come out to be minus 1 to the power k, where k is the number of primes dividing it. So this is 3 right now, and this value would come out to be minus 1 here. Did that clarify what I meant?
Yeah.
Okay. All right. So again, you guys, the reason we are studying Mobius functions because mu is multiplicative once again, and I think it's pretty obvious to see again why it is multiplicative. So again, we would consider two numbers m and n which are co-prime, and again these won't share any primes between them. So if m is a number which has a prime dividing it more than one time, then mn will also have a prime dividing it more than one time, and both these values would come out to be 0. Otherwise, both m and n have primes dividing it only one time, and since the GCD of these two numbers is equal to 1, therefore they do not share any primes. So if this has suppose say x primes and this had y primes, the value of mu mn would come out to be minus 1 to the power x plus y. X plus y primes would be dividing it, and yeah, that's the value. So yeah, mu is multiplicative. Another very interesting property of mu is that let's consider the sum of mu values for the divisors of a number. So if we want the sum of mu values for the divisor of n, then this is equal to 1 if n is equal to 1. Otherwise, this value is equal to 0. Yeah, I bet you guys understand what that is. Yeah, so that's the property. For developing an intuition, how this happens is that consider so for any number n, you would not consider any of the powers which are greater than 1 probably. So you just consider calculating the sum of mu values for n is equivalent to calculating the product of the primes dividing it. So for like n is equivalent to p1, p2, so on till pk. If n was of the form p1 to the power a1 and so on. So these two values are equivalent, like for with respect to the sum, because all the other powers which have any of the p values, pi values greater than 1, they would come out to be 0 here. Now let's see what happens here. So let's take a set which has 0 of the primes dividing it. So a divisor which has 0 of these primes dividing it. So the ways to select that is kc0 ways, and the value which would come out to be is -1 to the power 0, which is 1. So kc was 0. The next value would be -1 because we would select one prime out of this. So kc1 ways to select 1 primes, then plus kc2 ways to select 2 primes out of this, and so on till we select all the kck primes. Kck ways to select all the primes, and everyone knows this sum from JE, I guess, that the sum of the sum of the kci values for odd indices and the even indices for any k is same. So when you subtract this value, this sum turns out to be 0 over here. We can express this as a binomial formula for in case people don't remember it, and this value is equivalent to 1 minus 1 to the power k. Alright, everyone got this? I think everyone got it. Alright, so let's move on to why we study the Mobius function. So this topic is called Mobius Inversion. Okay, so Mobius inversion actually allows us to get some function out of, like, retrieve a function back basically. So let's define a function f. So we have a multiplicative function fn here, and we define, before we study Mobius inversion, let's define another function over here, capital Fn, and capital Fn is equal to sigma of the numbers that divide n and the value of f of d over here. Okay, and as it turns out, this function is multiplicative as well. If small f is multiplicative, then this capital F is multiplicative as well. How this happens is, I'll try and develop an intuition for this, is that we take capital F of Mn, and again we have sigma of, sorry about this, we have sigma of d divides Mn, f of Mn. And now we can express the sum of, like, in terms of the divisors which are co-prime to each other basically, right? Okay, so basically how that happens is, we know that m and n are co-prime whenever we considering multiplicative functions, right? So if d divides mn, then we can split D into two parts over here, D1 and D2. And these parts are split as such that D1 divides M and D2 divides N. And D1 and D2, both the product of it is equal to D. And you see why we can do this is because since these two are co-primes, the set of primes which divide D, they can be split into the set of primes which divide M and the set of primes which divide N, and these do not have any of the primes in common because M and N are co-prime. So we can always split any D into D1 and D2, right? And these are mutually exclusive sets. So let's just erase this part off. So we'll express this sum in a different way now. Okay, so the sum turns out to be sigma of D1 divides M and sigma of D2 divides, I'm sorry, yeah, this should have been D over here. I made a mistake there. Yeah, divides N, and this becomes f of D1 and f of D2, right? And now we know that these two do not have any primes in common, so we can split them out because f is small f is multiplicative over here. So we can make this D1 divides M and f of D1 out here, and D2 divides N and f of D2 here. Alright, and now it's pretty easy to see that this value is equal to, so you can compute the inner sum, that comes out to be f of capital F of N, and the outer sum, so capital F of N becomes a constant, it goes out, and the inner sum becomes f of small n. So f of n and capital F of n, and thus f of mn is multiplicative. Everyone got how this works? Okay, I think everyone got it. Okay, so back to Mobius inversion. So we're considering small f and capital F as we defined before, and the Mobius inversion formula says that this small f of n, this value is equal to sigma of d divides n mu of d into capital F and n by d. So using the capital, so if you have the sum function for any element, sum of divisors function for any multiplicative function, you can restore the multiplicative function using that, basically using the Mobius inversion function for it. Alright, so how does this work? Let's try and prove this. I think the proof is too long for this. You guys can look it up. If you guys have any doubt in the proof, you can just text me on FB. But yeah, but this is the formula which we would be using. Just see that we multiply the mu of d value with the n by d value of capital N. So if we have a product uv equal to n, so u goes to mu and v goes to capital F. All right, so we come down to the final topic for this. We will use Mobius inversion in the final topic as well. This is called a Dirichlet convolution. It's very similar to Mobius inversion. It's pretty much that, only convolution. And the Dirichlet convolution for any two functions, not just multiplicative functions, for any two functions is defined in this way. So it's not a property as such, it's just a term for a way to convolve things. And this is equal to sigma of uv is equal to n, and f of u multiplied by g of v. We call this value the Dirichlet convolution. Note that f and g are may or may not be related in any way. It doesn't matter, but this is how we define the Dirichlet convolution. So
What's written in the second bracket?
which one?
Yeah.
This is n. I'm sorry, just I'll write it better in a better way. Yeah, this is n. So f convolved with g, the function which results, the value of n in that function, that results to be the product of the sum of product of f of u into g of v, where u into v is equal to n of all the pairs, of all such uv pairs. All right, and u and v are integers here. That's to note here. How does Dirichlet convolution? So let's see some very common Dirichlet convolutions. So using the Mobius inversion property, which we just studied just now, we get that capital F into convolved with g, convolved with mu, this is equal to small f. So this is one of the Dirichlet. This is one Dirichlet convolution. So Mobius inversion is a type of Dirichlet convolution. And let's move on to the next page for this. So epsilon. I'll explain what these symbols mean right now. Into the identity function convolved with mu is equal to epsilon. Epsilon is 1 if n is equal to 1. Epsilon of n. Sorry, just a second. Epsilon of n is equal to 1 if n is equal to 1, otherwise 0. Alright, and the identity function is pretty simple. I is equal to 1 for all n greater than or equal to 1. Of course, n belongs to z. When we talk in number theory, everything belongs to z. So epsilon is equal to 1 star mu, 1 convolved with mu over here. So we're done with the content for this. Let's see how this manifests into some problems. All right, let me exit my full screen. Let's do the first problem here. You can open it in your computers, laptops as well. That's fine as well, but I'll show this statement here and read it out as well. So the first problem is called expected greatest common divisor. This is a problem from Cook-Off 2012, one of the Cook-Off in 2012. So the problem is as follows. You have k ranges of numbers. So you have a0, b0 as the first range, a2, a1, b1 as the second range, and so on till ak minus 1, bk minus 1. And from each of these ranges, you pick a random integer. So these ranges are inclusive ranges, okay? And you pick a random integer from each of these ranges, and you calculate the GCD between all these values, all the values which you get from each range. And what you want to do is you want to find the expected GCD value out of these ranges. All right, everyone got the problem? What is the expected GCD value? So if the expected GCD value, you can ignore this part for people who don't know this, but if you get the expected GCD value in the form of p by q, you have to answer it in terms of p plus q into n. You can read the statement yourself as well, but yeah. So that's the problem. Anyone has doubts in the problem? What the problem is? Okay, I'll give you guys 6 to 10 minutes to solve this problem, and then we'll discuss the solution. Okay. Did anyone get the solution? Okay. Did anyone make any progress? Like, what's the idea in general around here? Yeah.
I don't have an exact idea, but I mean, I barely have an idea at all. I think it's going to somehow decompose to like, we're going to want to check like, so the GCD can be between 1 and max AI comma, what is this here?
2e6, I think.
Yeah, whatever that is. So you can, iterance is going to be checking like, so case less than equal to 5, right? So checking each pentuplet of, because it'll come like, we can check in like something like log kind of thing, right? It'll dissolve into that. Check if the GCD of each pentuplet is equal to that. Not exactly that.
Okay. Okay.
And after
Yeah,
that, try to decompose it. But I'm
I think.
not sure how
okay,
to
so,
exactly.
Yeah, of course. So the idea is to see the number of tuples that have GCD equal to G. Yeah, you're right about that. But yeah, how do we do that? And apart from that, so I think for this particular problem, the k equal to 5, constraint, that's like that can be increased as well, not just limited to 5. It could have been 100 as well, or 200 as well. We'll move on to the solution and we'll talk about how. Okay, so yeah, does anyone have any doubts what he just said right now? I think everyone got. So the problem is calculating the expected sum. So the expected sum is of course the average of all the possible GCDs. So the sum of GCD sigma g for every possible tuple divided by the number of tuples. So the number of tuples is pretty easy to calculate, and that value is equal to the product of bi minus ai plus 1. So number of tuples this is equal to over all I. This is value equal to bi minus ai plus 1. Pretty straightforward to see. You can just pick bi minus ai plus 1 numbers from for each position of the tuple, and the product of it would be the number of possible tuples. Now, so the main part of the problem is calculating the sigma g, which is above it. And as Pranav rightly pointed out, we have to calculate the number of tuples where each g, like for each g, we have to calculate the number of tuples which have that GCD equal to that g. So let's rewrite this sum a bit. So sigma over all g, and we can see that by the constraints of this problem, this g won't exceed 2e5 here, because all the bi's values are maximum 2e5, and so g values will go from g equal to 1 to 2e5 max here. We can denote max as 2e5 over here. Okay, and the sum can be transformed into g into number of tuples which have GCD equal to I can never get the hang of this. GCD equal to G. Yeah. So how do we do this? So here's the magic of the problem. Here's the entire magic. If anyone was able to figure this out, then the problem is very, very easy. But it is very hard to figure it out. So do you guys remember that you could write any number n in a different way? Like any number n can be expressed in the form of sigma of d divided by n phi of n. I mentioned it earlier, and I purposely said that why would anyone write n in this way, because this was the key to this problem basically. So you can write g in this way in this problem, and this would make your life a lot easier here. So G becomes, so we could transform from G to D divide over, again the sum is over all G's max, but the sum becomes D divides G, phi of D into number of tuples of G, cube of G, right? But now we have an interesting way of rewriting this again, is that we can remove the G variable altogether from this. So this is also equivalent to sigma of D equals 1 till max. This is the major step in this, so if you guys don't get it, please say so. So D into so this value is equal to not D, this value is equal to phi of D multiplied by the number of tuples which have GCD with GCD such that D divides the GCD. Did everyone get how I rewrote, the rewrite, how I converted that sum to this sum? Is there any doubt with this? Okay, there is no doubt. So the problem is very direct right now, because now for each D you can calculate the number of tuples which it divides basically. Okay, I think there was, yeah, okay, Pranay was replying to that. Okay, so the number of tuples which which are divided by D, small d, and this is pretty easy to calculate, because let's say for a particular D you want to calculate the number of tuples which it divides. So you can go to the first tuple and you can do B1 divided by D. So these numbers divide minus A1 divided by D. So in the range A1 to B1 there would be B1 divided by D numbers and A1 divided by D numbers, plus in case A1 divides D as well, D divides A1 as well, then we would have subtracted that as well from the sum. So we need to check if A1 plus 1, if A1 modulo D is equal to 0. So this would, for a particular position of the tuple, this would give you the number of values for which D divides that value. And similarly, so you can do a product over all the i's here. So we can convert this to I over here over all k, and for each D you would get this value, and you can pre-calculate all the phi of D values over here and then just sum it up. So this algorithm turns out to be an O of max into log max algorithm. I'll explain how this log max comes from. So when you pre-calculate the phi of D values, you would want to construct a sieve for that. So the sieve stuff is pretty simple. So you can calculate that value in O of max for each of the so the sieve takes O of max log max time, and for the yeah, I think it's log. I'm sorry, I think it was a brain fart. It should be log max over here, log of log max. So the sieve takes O of max into log max time, and you can and after that you would have all the totient values here, and this takes just O of k time here. So it's O of max into log max plus O of max into k here. And I'll go over the code here. Did everyone get the logic behind here? Is any part unclear? Yeah.
Could you just re-explain how does this equate to it? The bi by d minus ai by d equates to phi d into number of tuples of GC?
So for a particular position in the tuple, so for a particular pair here, you could calculate the number of values which D divides. So that those values would be bi by D minus ai by D. So you would get some values, but this could be off by 1 as well. The case where it would be off by 1 is if ai is also divisible by D, so that value would get removed from here.
Yeah.
So you can get for a particular range, for one of the ranges, you can get the number of values which it divides. And if you multiply over all the ranges for a particular D, you would get the number of tuples that have a GCD which is divisible by D. So you get this value for a particular D, and you have pre-calculated phi of D here. So you get, in this way you can get it in O of max log max time, this sum.
So just one small thing, how do you do the so I don't know if I missed it, but how did you transition from like the number of tuples which are a multiple of GCD to the number ones which are just with exactly GCD?
Yeah, so initially you had, the key step was writing G equal to sigma of D divides G phi of D, right? This was the key step. And if you write it this way, so it was again the number of tuples which, so if we recall, like it would be a lot of effort to go back all the way there, but
no, I think I got it. I think I got it from that. I forgot about that one.
All right. Does anyone else have any doubt with this? Okay, I don't think anyone has it. All right. So the space is again O of n, O of max space, and O of max log max time here, log max time. So let's go over the code for this. Actually, I've written all the codes, my submissions on these problems. This is the modulo. This is a standard modular exponentiation function here. The primes array denotes which of these numbers are primes, which are not. If it is true, it is a prime. It is not a prime. We are doing a standard sieve over here. This array would store all the totient values, and this num array would be a helper array for calculating these totient values. We'll see how. So initialize all primes equal to true, totient of I equal to I, and num of I equal to I as well. So if a number is in the standard, just like the standard sieve, if a number is prime, mark all its multiples as false, and keep dividing that multiple by I till the point it is divisible by I, and remove all the factors of I from it, and multiply the totient with I minus 1 by I, so 1 minus 1 by I basically. Okay, and at the end you would be, if there is any num of I left with it, that means that there is a prime greater than square root of 2e5 left in that number basically, and the power of this prime would always be 1 basically. So you can again multiply it by 1 minus 1 by num of I, the totient values. So you iterate over it again. Is the totient calculation clear? How this happens in O of max log max time? Okay, I think it's clear to everyone. Yeah, so moving on, so now it's pretty simple. So you just take all the ranges in input. You calculate the product. So these variables are for prod variable is for a single iteration, and sum is the answer variable basically here. So for every possible divisor I go over all the tuples, all the positions in tuples, and calculate the number of values which are divisible by I in that range, in these lines, and I multiply by prod. So in this way we can get the tuples which are divisible by D here, which are divisible by I, and I multiply prod by totient of I, and add this to the sum. So in this way we have the sum here. The last part is just for the output purposes, so it's not related to here. Since it's a very old problem, there are some weird output constraints here, so that's just for that. But this is basically the code for the problem. All right, everyone got the code? I think everyone got the code. Okay, we move on to the next problem. We have 2 more problems here. This problem, and then there's one more problem. All right. So these problems will slightly get more and more difficult. This was the easiest one, I guess, so far. So the next problem is another code problem. This is from a lunchtime contest in 2014. So yeah, the problem statement is pretty small here. So you're given a sequence of numbers a1 and a2 and an, and you have to find the number of triples in this function such that in this array such that the GCD is equal to 1. Pretty straightforward problem. The constraints are 1e5 numbers and 1e6 is the maximum value. Again, I'll give you guys I guess 10 minutes, not 10 minutes, 7 minutes, because we're short on time here. 7 minutes to solve this one. I'm linking the problem again in chat. Okay. Someone wants to join. Okay, I'll let him. I've linked the problem in the chat as well if you want to see the statement yourself. Okay, does anyone have the solution to this? Or any idea in general? Okay, I guess, yeah. So I know the reason why anyone does not have any interesting ideas this time, because the first step of the problem is basically solves the entire problem. If you get the first step, you will get the entire problem in this one. So the entire game in this problem is how you express this problem itself. And the way you express it is, you have sigma of 1 less than equal to y less than j less than k less than equal to n. So the number of triples such that the epsilon of ai comma aj comma ak, this value. Did anyone think of this? And can everyone see why this is true? Okay, I think everyone can see why this is true. So if you have epsilon, yeah.
Wait, what is the epsilon function again?
So epsilon was 1 if x is equal to 1 and 0 otherwise.
Okay, so that's epsilon of GCD of AIJ.
Yes,
Okay.
Turn off
that's another
fix mic,
bracket.
fix mic.
That's another bracket inside it. Yeah. So epsilon of GCD of AI comes in. So it looks like a very okayish observation, but let's see how this turns out to solve our problem. So what's the one formula or one identity which we learned related to epsilon? Is the Dirichlet convolution of the identity function and the Mobius function is equal to epsilon. So I'm not writing this lower part here again and again. So identity Dirichlet, the Dirichlet convolution of identity and mu of AI a to ak, this value is the same as this value. And now we know that the identity function is always 1 for any integer, for any positive integer. So we can express this in terms of just mu again. So over all the pairs, all triples, I'll just write it as triple, over all triples, if you can recall what Dirichlet convolution means, this sum would become not this, just a second. So AI, AJ, AK. So all the divisors of the GCD, the mu value of the divisor, not, sorry, again, this, the mu value of the divisor. So this sum turns out to be this value actually. All right. How does this work now? So basically what you want to do is you want to calculate the number of so this value can also turn into be let's see again. So I'll erase this part. This value is also equal to d equal to 1, like the earlier problem, to max mu of d into the number of times it appears. So number n, where d divides the GCD of AI, AJ and AK. So like the last problem, once again we are at a similar situation, except instead of having phi of d here, we have mu of d here this time. And again, like the last problem, we can calculate, in fact we can calculate this very simply this time. So you can calculate again all the numbers in the array which are divisible by d and we can call this function as diff ct of d is the number of numbers of ai such that d divides ai, right? And it's pretty easy to see how we can choose triples from this. It's simply diff ct of d c3 here. Everyone clear so far? So this turns out to be a very simple sum actually. So this is again d is equal to 1 till max mu of d multiplied by diff ct of x c3. And I think everyone calculate this sum from here on. Does everyone get the logic? I'm sorry, this should be d, not x here. Diff ct of d c3. Does everyone get the logic? Okay, I think everyone gets the logic. So the code for this problem, let's move on to the code. So this is the code for the problem. Again, the same way to calculate, so for mu calculations we have prime divisors for which calculates the number of times the factor. Basically this calculates the factorization for each number, this array, and diff ct is the number of number of AIs which divides which I divides basically. So like we mentioned earlier, frequency, I think frequency, yeah, frequency is the number of times each number occurs in the array. So yeah, so again, like the last example, we have a num of I array which serves the same purpose like last time basically. So we do the same stuff, we factorize it so far, and we push I comma ct into the factorization of I star j. And if num of I at the end of it is greater than 1, we push num of I comma 1 at the end of it. So this way we can calculate the factorization of each number. Now we call precalc diff before doing anything, and this will calculate the diff ct values for each number here. And the way it does it's pretty simple. You initialize the frequency array, and for you iterate over all the multiples of each I. This will take max log max time, and you add frequency of I star j to each I here. Alright, so this is done. NC3 is just a function, a helper function for me to use NC3 here, and mu returns the Mobius function for x value. So you can iterate over the prime factorization, just check if it is greater than 1 at any point. If it is, then return 0, otherwise just multiply with -1 and return the value. And there onwards it's pretty straightforward, just calculate the sum from there. Everyone got how this is done? Is there any doubt in this? Okay, I don't think there's any doubt. Let's move on to the final problem for today. This will probably be the hardest problem which we do today. Like not seemingly, it's not seemingly the hardest problem, but it was in my opinion the hardest problem of the set. So this is called LCMSUM. It's a classical problem on Spoj. I share the link in the chat again. I hope you guys have time today. I'm extending by like around 15 minutes, I think. Yeah. Okay, so this is the final problem. So the problem is very straightforward. You are given t test cases, 5 test cases, and for each test case you have to calculate the sum of LCM values from LCM of 1 comma n, LCM of 2 comma n till LCM of n comma n. For each test case you will be given an n value here, and n is up to 1e6. Yeah. This is a pretty old problem. This is a 2010 problem, but it's a solid problem in my opinion. Yeah, so I'll give you guys another. I'm sorry, like it's not to disrespect the problem. The problem is pretty hard. All the problems are pretty hard. I know that, but we just short on time. That's why I'm giving you so less time. So 7 minutes again, and let's see. All right, anyone with any progress? The problem? Anyone? Like, I know this is a very difficult problem to simplify. There's a lot of steps for this one. All right, let's do it then. Okay, so the problem is, like always, we can express everything lies in the mathematics parts of this. The end part of these problems is usually very simple to implement. So the problem is this square bracket is the LCM here. That's my symbologies, but yeah. So the LCM is obviously equal to the product of numbers divided by the GCD of the two numbers. So we can express this again in terms of for I n divided by the GC of I and n. Right? Now how to move on from here? Now for each so this value would always be a factor of n, obviously. So we could actually iterate over all the factors of n. For expressing this sum, we could actually iterate over all the factors of n and see for how many i's does the GCD of I comma n equals to a particular factor, basically. So let's rewrite this sum again. So this becomes, I'm sorry, yeah, so this becomes d divides n, so the divisors of n, and I equals 1 till n, such that the GCD, such that I comma n is equal to d, and this value becomes I n divided by d here. All right. Okay. So now whatever value we get, remaining value which we get, this can be expressed. So this value with the GCD of the value would always be equal to 1, the remaining value. So let's rewrite this as so we take out the n basically outside because it's a constant over here, and again, so write this as I by d, I equals 1 till n, I by I GCD d, I GCD n is equal to 1, d over here, and now we can express this value over here in a different way. Let's call this value as a, and now try expressing this sum instead of in I. We try it expressing in terms of a, basically, not i's. So again, d n a is less than equal to n by d. Do you see this value would always be less than equal to n by d, because the maximum value I can take is n, so it would always range from 1 to n by d, right? And the other condition is that since d is the GCD of I comma k or I comma n, that means that the GCD of a comma the remaining part of I, so the GCD of just a second, yeah, so the GCD of a comma n by d, this would always be 1. This would always be 1, and you're summing over all such a's here. Did everyone get this? Like how this happened here? Okay, everyone got it. So let's do one thing. We express this entire thing. Okay, wait a second. So we express this entire thing as some function f of d, basically. So okay, so I'll erase this part again. I hope you guys noted it down. So this becomes sum d divides n of f of d here. All right. And now how do we have to calculate this f of d value basically. That's the entire problem now. Okay, now here comes the, I would say, magic part here. So let's try see this. So if there are two numbers x and k and the GCD of these two values is equal to 1, then k minus x and x, these values would always also have a GCD equal to 1. Does everyone see why? The GCD would be 1 again, because if the GCD was some value d basically, then for this value would be d, then if you can divide these both with d, then k is divisible by d, so that means this value would also be divisible by d, and that means x would have to be divisible by d, and that means x comma d, the GCD between those two elements, would become d, and that's not possible because we stated that x comma d have a k have a GCD equal to 1. So that means that there's a contradiction, and k minus x comma x would also always be co-prime if x and k are co-prime. So now how do we use this basically? So if let's express if sigma of fx, so let's write it in this way. So sigma of, we're writing f of x basically. So if x is less than equal to k and x comma k, that was what we discussed just right now. K was n by d here, right? So it's the same thing here. So so for any general f of k here, we're calculating for that value. So if we have to calculate this value, this was f of x, f of k here, then this value is also equal to k minus x, x less than equal to k, and xk. Does everyone get this? Because if x is one of the numbers which holds this properties, k minus x would also be one such number. So this is a symmetric formula. So that means that this sum and this sum are both equal. And now using these two values, we can actually add them. So this value sigma x is less than equal to, so 2 into sigma x, we add basically this value to both sides of the equation. X comma k is equal to sigma of k, x less than equal to k, x comma k is equal to 1, right? And you can divide by 2 on both sides, and you would get sigma x, x less than equal to k, x comma k equals 1 equals k by 2, and with the same property. And now if you notice this property, this rings a lot of bells here. This is equivalent to phi of, so since this is a constant value, this will become sigma of 1 with this property over here, and this value is exactly equal to phi of k over here. So this sum, so f of d works out to be k into so f of k works out to be k by 2 into phi of k basically. Does everyone get how we reached here?
Yes.
All right. So now to plug it back into the answer. So the answer is sigma of d divides n d into phi of d divided by 2. This is the solution to the problem. again, you can calculate all the values in n log n time and O of n space. And yeah, that's it for the problem. Just for the problem, I'm not sure why this happened, but just for this problem, you have to assume phi of 1 is equal to 2. This is a hack for the problem. This is just a hacky way to work around it, because the reason is that if you don't assume this, then if you try to answer query phi 1, then query for n equal to 1, you will get a non-integral answer here. You will get half as the answer. And this phi 1 value also adds up to other n values as well. So you need to assume phi of 1 equal to 2 here. It's just a hack, but otherwise it's the same here. Does everyone get the solution? Okay, I think everyone gets it. So here's the code. I think code wise this is the shortest problem of 3, but logic wise this was probably the hardest one, because it involved a lot of manipulation magic. So again, same things, primes, num, totient function, and the answer value is we're pre-calculating all the answers here basically. So we're pre-calculating the sum here, this sum here. Oh yeah, right, so I forgot the n outside. I forgot the n that I took outside. Yeah, so it should be n by n outside, and n by 2 into 5 only. Yeah, so we calculate this sum for each, pre-calculate each sum for each possible n, and when we have to answer queries, we just multiply it by n and divide by 2 and answer it. D into 5 by d, this sum we pre-calculate for everything. Okay, so right, so the answer calculation is pretty simple like the last problems. Just notice that I do a plus equals 2 here for corresponding to the I equals 1 value. I set answer of 1 equal to 2 here. That's the only thing that I do extra in this problem. Rest is same. Alright, so that's it for the problem. That's it for the class actually as well. Does anyone have any doubts in general for this, or should we end the session? Okay, I think no one has any doubts. Alright, thanks for attending, guys. It was very fun. I hope you guys learned something too. Alright, bye.